Good morning, Monday morning. Welcome to Wk04, week 4. I've been sent quite a bit of emails regarding homework 1 and homework 2, and very similar question has been asked. I'm going to do 3 questions for today, 2 from homework 1 and 1 from homework 2. No, 1 from homework 1, 2 from homework 2. Okay, so that's what I'm going to do today. And at the same time, on the side, I will start writing summary sheet. How many of you know how to write summary sheet? And how many of you have been writing summary sheet? Fantastic. Okay, summary sheet is very important in tertiary education. Right. So the question is going to attempt, I know the solution is out, okay, but I want to explain why it is like that. Okay, so these are the 3 problems that we are going to go for. Okay, so question number 1 is from homework 1, question number 2 from homework 2, question number 3 from homework 2. Okay, so let's do this question first. Now, it's normal if you find this question overwhelming the first time you see it. How many of you find it overwhelming? I did find overwhelming when I see it the first time. Okay, right. The thing about questions like that, I'm going to show you how is it actually solved. And more important to me is you understand why. Okay, rather than, oh, I've done it, this is the correct answer, okay, move on. No. Okay, let's not do like that. Okay, now, the card has a mass M and it is attached to 2 springs. Determine the natural frequency when both spring K1, K2 are unstretched, when the card is in equilibrium position, and B, 2 springs, each having a stiffness of K1 equal to K2 is equal to K, unstretched length of L0 and a stretched length of L when the card is in the equilibrium position. If the card is displaced a distance of X equal to X0 such that both spring remains in tension. Okay, so I put hint, must draw multi-body free body diagram to analyze the direction of the spring force. So the hint are always the one that really help a lot. Okay. So let's start. What did I teach? Okay. So if you go back to a notes, okay. So I'm going to write a summary over here. Okay. So the first thing is what? The spring force always opposed to the applied direction or applied force. Okay. And then you will come out, remember how I taught you all how to draw multi-body free body diagram? So you remind yourself, multi-body free body diagram. Remember we did this, so remember when we draw this, if we have a, let's draw in a conventional way, right? When you have a spring and damper system, okay, and when this is Y, right? So when the spring is in tension, right? If the spring is in tension, so first we go for tension first. If the spring is in tension, what do? The spring grow what? Longer, yes or no? So this is in tension, right? So if this is my force P, and then with the mass, this has to oppose. So you write over here, this is based on what? Newton's switch law. right? And then you can add in another one, okay? You can add in what if it gone compression. Okay, so you write, okay, if it's in compression, what will happen? So if this is in going through compression, right? So this is the spring in compression, action equal reaction, same in magnitude, different in what direction? We clear? Okay. So from here, can you think of any more? Oh, cannot think of any more. Move on. Okay. To test your summary sheet, how good it is dependent on what? How you apply your summary sheet based on a what? A question. Are we clear? And this summary sheet is not I do it now, you'll be always like that. No. Summary sheet is continuously what? Enhance or continuously what? Improve. Are we clear? Okay. Then you apply what we learned from here. Okay. So case number A. I'll go to a different mode. I think drawing in this mode is okay. You can see the blue line. Yes. Very good. Okay. So number A. The first part of the question states where what? K1 and K2 are what? Unstretched. Okay. And we have to determine, and then we have to find what is our omega n. And first of all, we know omega n is equal to square root K over M. Okay. So given the answer, omega n for question 1 is K1 plus K2 over M. And then when it is B is equal to 2K over M. Okay. Right. So now we start sketching. Okay. So we sketch. So we know that this is our right. And then we have our block. And then we have this. And then we are given that this is our K2. And this is our K1. Okay. And the first part, it says the what? So this is our equilibrium position. Okay. And it states that the springs are what? Are unstretched. Okay. So over here, when we draw our free body diagram, right? We know that K2 x, okay, is equal to 0. K1x is equal to 0. Okay. So 0 means what? There's no force at all. Are we clear? Okay. So the next part of the question say, what if now, right, we are going to move this. Okay, we are now going to move this. And we are going to move this towards the right. Can you see it's been moved towards the right? And it's been moved towards the right by a distance of what? A distance of x. Okay. So these two walls are still fixed over here. So now, K2 now will be under what? Anyone? You can call it tensile, or you can call it what? Compression. And then K1 is under what? Under compression. Okay, so this is our K2, and this is your what? K1. Okay. Now, to get K2 to be in compression, the force, the spring force, has to go towards the right or towards the left. Anyone? If I want K2 to be in tensile, the force has to be towards the which direction? Right. Am I right? So when you pull this, it's going what? Longer. Okay. Understand? Now, if we look on the spring on the right-hand side now, which corresponds to K1, to make it compression, the spring has to be in which direction? Was the right also? Okay. Okay. And then we apply Newton's third law, action equal to reaction, same in magnitude, different in what? Direction. So this corresponds to K2 X or X. I won't call it X2, K2X. And this corresponds to K1X. Okay. So from here, we look at the body. Okay, we look at the mass. Okay, consider the mass. Okay, so now we're going to sketch the mass. Okay, so after knowing the mass, we know that over here, this will be what? K2X, and this will be what? K1X, and we push X towards the right direction. Okay. So the next thing we need to do is net force to accelerate the mass is equal to mx double dot dot. Okay. Net force acting on spring this will be equal to minus K1x minus K2 what? X. Okay. Now, why is it minus? Anyone? Why is it not plus? Yes. Yeah, opposing the direction of the applied force or the applied direction. And it's all dependent on what? Can you see this? This also declare what? What did this declare? This also declare what? That X, this direction is what? Positive. Are we clear? Right? So is this important? Oh, you write down here. Oh yeah, this is important. So you go back to your summary sheet. Okay. You put positive in X direction is this way. Positive in Y direction is this way. Are we clear? Okay, so this will affect the vector of the displacement. Are we clear? Right? So this is the next point that we what? We add. Okay? Then we come back here again. Okay, now we have everything. The next thing that we're going to write now is we're going to write out the equation. So it's equal to mx double dot is equal to minus K1x plus or minus by what? So mx double dot is equal to plus by K1x plus by K2x. The whole thing is equal to 0. So finally, so from here, we found out that omega n